This is the first part of a review for the second exam in COMP360 Programming Languages at North Carolina A&T State University. Was that Plato or Yoda? The second exam is this Friday, March 27th, from 2 o'clock to 3 o'clock. You have to be logged into Blackboard between those times. It's going to be an online exam. Topics include everything since the first exam. In particular, we'll cover parameter passing paradigms, object-oriented programming, including constructors, overloading, overriding, polymorphism. We'll also cover garbage collection, tail recursion, and generics. The exam uses examples in a new language I just invented called Examgol. Unless otherwise indicated, Examgol works exactly the same as Java, but the syntax is different. There are no semicolons, no curly brackets. Like Python, indenting determines the level of nesting. So if something's indented, it's part of the function or a constructor at that level. Constructors don't have a constructor name. Instead, they're called constructor. And functions start with the word function. There's going to be a lot of Examgol on the second exam. Here's an example of Examgol and the same program in Java. You'll notice the syntax is different. In Examgol, you specify the variable name followed by a colon and the data type. Constructors start with the word constructor, don't have a method name because the method name has to be the same as the name of the class. Functions start with the word function. If they return a value, then after the right parentheses will be colon and the data type. Hey, I could write a program that converts Examgol to Java. Dr. Williams would be proud of a COMP360 student who does that. There are several different means by passing parameters to a method from a calling program. You can call by reference, value in, or value in and out, result, by constant value, and by name. When a parameter is called, or a method is called, information is pushed on the stack. In this case, looking from the bottom up, we start pushing the parameter values on the stack. If it is a simple value like an int or a double, it pushes the value of that variable onto the stack. If you're passing by a reference, or in Java, if you're passing a object or an array, then you push the address of the value on the stack. The call instruction pushes the return address in the stack and jumps into the method. The method then allocates space for the frame pointer, which points to the previous activation frame. This makes it easy to do a traceback from method to method. And then local variables are allocated on the stack. Here's an example where we're going to call a function passing it a widget or a value by reference and a simple integer. The first value pushed on the stack is the second parameter. That way the first parameter will be on the top of the stack. In this example, we're using an Intel-like stack that grows downward. So since the first example was an int, it pushes the value of the integer. The second parameter was an object, so it pushes the address of the object on the stack. And then it executes the call instruction. The call instruction pushes the return address on the stack and jumps into the function. And then links the activation record to the previous activation record. And then local variables are allocated. When the function wants to return, it deallocates the space for the local variables and the activation record by adjusting the address of the stack. And then does a return, which pops the return address off the stack and jumps to that location, which is the instruction after the initial call instruction. You now have two values on the stack that were pushed there as parameters. The calling program then removes those values so the stack is just as it was before the method call. Java uses call by value in, answer B, for simple variables. Objects are passed by reference. Some languages, such as C++ and C, require the user to explicitly return or release memory values that are acquired dynamically. This requires more code to maintain. In other words, you have to write the code to actually release the values or free them. And many errors can occur. If you free the object too soon, then now you have a pointer that's pointing to something that doesn't exist. If you free an object too late, well, you're wasting space, and perhaps you might never free it, in which case the object stays there in memory for the length of the program. Some programs that run for a long time get larger and larger as data values are never freed. On the other hand, efficiency can be very high. The programmer knows as soon as they're done with an object and it can free it. So it doesn't have to wait for garbage collection to come around and free it sometime in the future. This gives the programmers control of the memory management system. Garbage collection, on the other hand, does this automatically. Programmers do not have to release memory. It's automatically picked up by the garbage collection system when it can no longer be referenced. This eliminates all sorts of possibilities for errors. Many languages such as Java, C# now use automated garbage collecting. There are challenges in it. It's not always as efficient. Memory systems tend to get larger before the system decides to call garbage collections. Isn't always immediately aware that an object is unreachable. And then there's the time it takes for the garbage collectors to run. Some garbage collectors have been designed to run in parallel using dual core processors. They run in the other core to do the garbage collection while the program continues to run in the first core. Hey, I like garbage. You could be a garbage collector. Here are the 4 pillars of object-oriented programming: inheritance, encapsulation, abstraction, and polymorphism. Polymorphism is the ability for a program to vary depending on the type of data you're using. You have parameter polymorphism, which means you can have the same method name with different parameters. So you can call the method with different types of parameters. That allows you to have the same method. You can call it with a double, you can call it with an int, you can call it with a long. You don't have to have a separate method for each data type. Here's an example of polymorphism. We have the method doIt, and it can take either a triangle object or a square object. So we can call doIt with whatever object we happen to have. Encapsulation is the concept of keeping the information inside the object free from the access from outside the object. So programmers provide an interface, that is the method headers, on how you can access this object, but programmers do not have to see the inner workings of the object. There are several ways you can restrict things in Java and in C++. Private means only methods within this class can access this data value. Public means that any part of the program can access the internal data parts of this program. Protected means that classes that extend or inherit from this object can use these data values, but otherwise other parts of the program cannot. And in Java, we have the default, which means only methods in the same package can access these data values. Abstraction is the idea of keeping things hidden, that it doesn't matter to the user of the data object how it works, it just matters what it does. Binding is the idea of when you attach a name to a value. It can be done at many different times in a program. There are several times when you can attach an idea or a name to a number. At language design time, you might decide that ints are always 32 bits and longs are always 32 bits. That's the way it is in Java. Sometimes similar values are assigned at language implementation time. In C or C++, the length of an integer and the length of a long are determined when you build the compiler. The C++ language requirements don't specify the exact length of an int or long as a long is not shorter than an int and an int is not shorter than a short. When you write the program, you declare variables and you attach values to those variables. When the program is compiled, those variables are then assigned a relative address, an address based on the beginning of that file or that module. Then when the program is linked together, all the files or modules are connected together and the addresses of the variables and methods are decided relative to the beginning of the program. When the operating system loads your program into memory, the address of the variables and methods are assigned to physical locations in the machine. When you call a method, the values of the method are determined by the calling program. In other words, when you write a method, you declare parameters and you assume that they're going to have values that will be given to them when the method is called. So they're bound at method entry. You can kind of group the binding into static and dynamic. Static being things that are bound before the program runs, and dynamic being things that are bound while the program is running. For instance, parameter values are dynamic. They are bound when the program is run. Then there's the lifetime of a binding. You want to make sure that the lifetime of the binding matches the lifetime of the object. If the object outlives the binding, then it's garbage. And if the binding outlives the object, then it's a dangling reference. It's a reference to an object that doesn't exist. In general, earlier bindings are more efficient. That is, if the compiler can determine exactly where this variable is going to be located, then it doesn't have to try to calculate it during the execution. On the other hand, later bindings are more flexible. In polymorphism, you might have a method that you call that you aren't exactly sure if it's the method of the parent class or the method of the child class, and that has to be determined at runtime. Compiled languages often have a little earlier binding times. Interpreted languages might have later binding times. Be sure to view part 2 of the second exam review. It's got to be better than this. Remember, the second exam is Friday, March 27th from 2 to 3 o'clock.